Dear all, welcome to the 2025 edition of the DDS webinar series. So it's my pleasure to introduce Jan Sieber. I'm pretty sure that for most of you there is no introduction needed, as many of us know Jan very well. So Jan has a very international career. He did his PhD in Berlin at Humboldt University, and then he has worked at many very good places in Bristol, Aberdeen, Portsmouth, and currently he's professor at the University of Exeter. So Jan's research spans a very long range of topics. He has theoretical contributions. He worked on computational tools and software, and also a variety on applications. And what I appreciate a lot is that in all the work, a unifying element are the very strong mathematical foundation. And that's the way we want things to happen. So thank you very much, Jan. So you have the floor to kick off the webinar series of this year with a talk on numerical bifurcation analysis of Delay equations. Please go ahead.
Okay, so thanks, Wim. I hope you can all hear me. And thanks to the colleagues in Michigan and also to Wim for organizing this. And whoever in the United States who had to get up early. So my plan today would be, okay, so to talk about developments more or less over the past decade of DD-BIF tool, which is a tool that is used for numerical bifurcation analysis in delay equations. And so I will just just for context, so this is a piece of software, and so some of you may have used it, and I just discuss various, old features and new features, and just give a few demonstrations. And so the basic underlying code is at this link that I put here, and the demos that I have today, I put them separately into some publicly available GitHub folder in case you just anybody wants to just see how it works or just check my working. Okay. So let me just. So by the way, I can watch the chat. So in case there's a question in the chat, I may be able to see that. So yeah, so what I do is just I start with one slide, just DD-BIF tools history, and then a few things that have been newly introduced over the past 10 or so years. So I may have talked about this at various occasions, but I here just summarize this. So some things like neutral equations or implicitly given delays or normal forms of equilibria, then symmetries, if you have a problem with symmetries, then distributed or delays and renewal equations, and then I summarize with a few okay, so these are features, but then while working on this, anybody who tries to use it may immediately encounter problems, and I just list one very common problem I just discussed at the end. Okay? So this is the plan. So let me go through this. So yes, so the tool itself was originally developed by the colleagues in Leuven. And so I think Koen Engelbox was a PhD student of Dirk Rose when he basically developed the code from scratch, as far as I understand. And so that base that's what it still more or less is. I then 10 years later, so Koen finished his PhD with a more or less complete piece of work. And then I took it over 10 years later, more or less on request of, I think, Gabor Oros, because everybody had a few additions. And so I just tried to collect them, and Giovanni Zamai then basically gave me permission to continue basically maintaining this. Okay. And so what's the kind of problems that it can study? So I just put the set of equations that you can study with this here. So it would be a system with delay, so it's a differential equation with a delay. And these delays can be, so there can be multiple delays. They're usually treated as discrete delays. So yeah, m finitely many delays. And so each delay can be a function of the system parameters, which would be p, or previously defined state. So this is kind of a recursive definition. As you can see, the first delay can depend on x of t, the next one on x of t and x of t minus 1, etc. And an important feature is that there can be a matrix M in front, and that matrix M, so it's a constant matrix, can be singular, which allows to then, I will discuss this, to have either neutral equations or other features. Okay. So this is the kind of setup. And so the various contributions, so what I mentioned today, so this is not not all like invented by me, or mostly it comes from various colleagues. So here's basically the list of the features. And as you can see, so the original, like the core features were implemented by originally Kuhn and then Giovanni, and okay, so it's performing bifurcation analysis, just to clarify. So this is not a tool for solving initial value problems. And generally, solving initial value problems for delay equations can turn out to be more difficult than doing bifurcation analysis, because then you have trouble with like what is an appropriate set of history segments that you start from. Okay, so yeah, so you can track equilibria, you can check determine numerical their stability. Then there are the few most common bifurcations which you can detect and track in several parameters for periodic orbits, so they get discretized. You can track them, you can find their stability. That was already all done by Kuhn. And then Giovanni implemented something special on connecting orbits, which is this is more or less still in its original state. So then I started out adding the local bifurcations of periodic orbits, which is a common task you want to perform, to just track, I don't know, folds of periodic orbits or period doublings and things like that. And then the colleagues from Utrecht added normal form analysis, like the criticality Hopf bifurcation. So this is done by, so I list here, so Michael Boschardt has been a PhD student. So it's more or less like the approach by Yuri Kuznetsov. And so implementation of neutral delay differential equations was done by several colleagues independently, because they had problems that were, of this type. So Dave Barton and Soazic Thierrien, and then the colleagues Hessel, Javolies, and Gurevich, they are optics researchers. They had problems in this area. Okay, so I'd like to start just to show more or less a standard example, or nearly standard example, which is so this is a differential delay differential algebraic equation, if you like. And this is a very typical problem that can happen, where so you have this is a classical problem by Hans Otto Walter, which is where the delay is given implicitly by a function by an equation where the state enters. Okay, so this is a toy example that was hooked up by Hans Otto Walter. I think I view this as a simplified version of a more realistic example that was studied by Tamás Insberger, where you have a turning problem which is of similar type. It's a more complicated equation. So this is a simple example. So you are in a position and you want to control where you are by just sending a signal to a wall, and you measure the travel time, and you adjust your position depending on that travel time signal with just a proportional. Basically, this is a proportional controller here. Okay, so you want to be at the position x ref, and so you just know how long it would take for the signal to travel, and then you adjust. So C is the travel speed of the signal, and then you adjust it with some control gain. So it's a simple toy model. It's the first order. You just treat yourself as a first order system, no inertia. And so the important thing is that the travel time, which is, so there's a reaction delay, which is constant. Okay, so you take a while to react. But then, okay, the travel time enters here, and the travel time is, of course, given by the sum of like where you've been, like when the signal was sent out, plus where you're now, and then this gets added up, right? So if you just look at this, so let me just show, okay, so how this would look like in practice. If I just no, here. So I hope you can see now MATLAB a little bit. Okay, so the way this would be set up, so you relatively easily define the equation, which I think you can see here. I hope you can see it here. Okay, and so it's recommended that you provide derivatives, which look like this in this case. Okay, so you can provide directional derivatives. You define your delays as functions. So here you have two delays. This is a square bracket, like a bracket. So this is the first delay, which depends on parameters and state, and then the second depends on parameter and state, and that happens to be a state variable now. Again, you give some derivatives, and then you set up, okay, there's a standard Didi-Biftul way of setting up the problem, and then you choose some initial parameters and some initial state for your equilibrium, and then you run and find the equilibrium. I continue this in the delay, and of course the location of the equilibrium does not depend on the delay, but as you go along, you detect various Hopf bifurcations which are printed out here. And as you can see, there are 3 hop verifications, and you detect whether they are sub or supercritical, well, with these Lyapunov coefficients. Okay, so then you might take one of the hop verifications and continue in 2 parameters. Let me do that now. So that would be the delay, the direction delay, and the control gain gives you a curve in 2 parameters. So you're below that region, your equilibrium is stable. Above it, it's unstable. Okay, and then like you check if that curve is sub or supercritical. That takes a while, and while it's doing that, it detects there are two points where the Hopf bifurcation changes its criticality. Okay, they are somewhere along the curve, and so then if you know some bifurcation theory, you may know that at this point, family of of folds of periodic orbits should branch off. So it's like there's some coexistence between oscillation and the stable equilibrium in along some part of the curve. And so branching off from that was implemented by the colleagues from Utrecht. Let me just try that. So the branching off is hard because this is a singular problem there, and sometimes it works. There are some warnings. And so now you see close to here, it starts to continue a lot slower because these are now periodic orbits. So these are periodic orbits that are themselves at a saddle node bifurcation of periodic orbits. And it tracks it, and it stays pretty close to the fold. So there's a tiny region of bistability. So the gap between the 2 curves is the region of bistability. Okay, and so if you plot that, that's how it looks like. Okay, we have a fold of periodic orbits, tiny region of bistability, and then the region of stability of the equilibrium is below the green curve. Okay, so now if you just want to branch off just periodic orbits of the first Hopf bifurcation, this is a single parameter continuation. So we do notice that we stop at some point simply because what happens there is that, let me just plot this. Basically our delay is state dependent and it reaches 0, which basically means we hit the wall. Okay. And what happens even further before, this is a typical scenario when you have state dependent delays, is that the derivative of the delay is bigger than 1. Okay. And that happens at this point. There, the derivative of the delay is exactly 1, which means you're moving faster than the signal speed. So if the signal was sound, you basically move at this point supersonic. So that makes the model unrealistic. And so, for example, what you can do also just with tracking this curve, you can just track in 2 parameters the periodic orbit where the maximum of the derivative, of the speed of the derivative, is equal to 1. So that's the boundary of the validity of the model, if you like. So this would be, I'm not sure, in piecewise smooth dynamic systems, people will call this a grazing bifurcation. Okay. And so that curve is also pretty close to the Hopf bifurcation. So it's slightly beyond the Hopf bifurcation, as you can see. So we track this in 2 parameters. And so that's how you just gradually build up the bifurcation diagram. Okay? So just a little demonstration. And if we just plot then the final diagram, it should look like this. We zoom in, you may see here this is close. So we have the Hopf bifurcation, and shortly afterwards we immediately reach, let's call it where the travel speed of yourself becomes basically faster than this travel speed of the signal, which makes the model unrealistic. And so here you can also see where the region of bistability develops. Okay, so this is a quick run through. Okay, so this is how this bifurcation diagram gets set up. So this is how you typically work. Okay, and so here's a more serious scenario. So I should mention like a large part of users of this tool are optics researchers in optics, and these are also some of the most challenging problems because speed of light is so incredibly slow that the delay is almost always unmanageably large. Okay, And so here, this is, for example, this is really a neutral delay differential equation, where you can see the second part is the neutral part, which is just a difference equation. And then you have the differential equation. And so there's a very complicated bifurcation diagram. Okay, so this was the problem on which the colleagues developed the code for neutral differential equation. So this is how we can deal with neutral delay differential equation or implicit differential equations, right? Let me just now briefly mention, so this has been developed already a while ago, this normal form analysis, as you have seen. So as I said, so this was done by the colleagues in Utrecht, in Utrecht. Yeah? So I think Yuri Kuznetsov was so he had this knowledge from the ODE theory, and I think Sebastian Janssen was developing this as part of his PhD research, like a general formalism, how you can translate this, how you can apply this to delay differential equations. And the beauty of their approach is that all the formulas look exactly like the ones for ordinary differential equations. So what I put up here, okay, so you expand your right-hand side, and all of these are then abstract functionals. Okay, the A is an abstract linear functional, the F is an abstract nonlinear functional, and so then you expand that F into higher order terms. And you can keep your singular M here, that's totally fine. So you get your characteristic matrix. And then the formula for example, for the criticality of the Hopf bifurcation looks exactly like for ordinary differential equations, except that all the eigenvectors are, of course, now functions. And of course, then they get, so they are arguments of your abstract functional. And that is it. So you get your normal form coefficients. If you just look up like a classical ODE tool, such as MATCONT, you would see exactly the same formula. Okay. And so then this is their simple expression for this coefficient that I had shown in my computation. So this tells us if the Hopf bifurcation is sub or supercritical. So that means the periodic orbits that branch off are stable or unstable. So this is it's quite beautifully implemented. Like the way their formulas are written is that they automatically work for neutral delay differential equations or for state-dependent delay differential equations. So even though their underlying theory in the paper is not covering that part of that type of equations, okay? But the formulas apply. Okay? Nice. So here's the example. So here's the plot. As you can see, so this is this L1 that as you go along the Hopf bifurcation, which is the blue curve here, which turns up, and you can see that the Hopf bifurcation is supercritical, and then it crosses, it becomes subcritical, and then becomes very. So these are the special points that were detected. So it works out of the box, and it just applies this formula after you detected the Hopf bifurcation. So that's what you can do. So now I'd like to switch like the third topic, which is somewhat say somewhat newer. So that typically what you may encounter in applications is that your problem has a symmetry, and there are two types of symmetries. There are continuous symmetries and there are discrete symmetries. So and two typical continuous symmetries that are encountered is so there's what's called rotational symmetry, which is that so these are the simplest possible symmetries that can occur, which is where, well, some variables are just like so basically the way it works is you have some variable, in this case it's complex, and if E of t is a solution of your problem, then any multiplication with a complex number of modulus 1 is also a solution. So that is it is so typical in optics that even the original code by Kuhn and Engelbrecht had drilled a hole into the dbif tool to just make sure that it can be applied to this kind of problems. Okay, so now this is done in a more general way that you can more or less, as long as you have you have to have the so-called generator of your symmetry, and then you can impose additional conditions. You should be able to more or less treat arbitrary symmetries. So a very common other symmetry is translational symmetry. So that occurs. So this is it's surprisingly common that you have a distributed delay in your equation, but where the kernel or the nonlinear function here is homogeneous. So it does not depend explicitly on the S here. Okay, so if you have that, then of course you can simplify your problem by. So here's an example. I just illustrated this with an example. Okay, so this is a renewal equation for some age-structured population. I picked this up from one of Dimitri Breda's analysis papers. So it looks like this. You see, this is a renewal equation. So you've got b of t is equal to some integral over the past of a function of b of t. And of course, this can be simplified. What you do is you just introduce the integrand here. Okay, so it just is basically the right-hand side of a differential equation. So y dot equals the integrand. So then y is, of course, the integral. And so that means that the integral that you have here over this finite from 1 to tau is, of course, just a difference between y of t minus tau and y of t minus 1. Right? And so if you do this, then, well, so this gives you a translation symmetry, because if y is a solution, then any constant, shifting the y by a constant is also a solution. And in order to remedy this degeneracy, what you do is, okay, so you just introduce an artificial parameter, which is in this case here, which I call c, which is making the, okay, so what happens here is you get this drift. So this compensates for the drift in our when we just do the integration. Okay, so this c basically has to be adjusted such that, for example, for a periodic orbit, our y is also periodic, because generally it wouldn't be periodic. Okay, and so then you just compensate. So this, of course, then the y is no longer the integral, but then you just subtract this constant term c times integral length here. So this is the typical way. So whenever you have a continuous symmetry, there are these artificial parameters that one has to introduce, and one has to also introduce artificial conditions. In this case, for example, it's an arbitrary. You just pick the y. Okay, so you just pick the y at 0, could be 0, for example, to pick a particular solution. And so that works out of the box. So very commonly, if you have these kind of simple distributed delays, you can just eliminate them and replace them with discrete delays. Okay, so this would be a discrete differential equation with a discrete delay. Okay, so that is continuous symmetries. Now for discrete symmetries, this is something that, Asim, he has just finished his PhD here in Exeter. So this is something that he had looked at. So discrete symmetries are also quite common. I mean, people might want to study, say, for example, networks of oscillators or networks of something. And so then the default situation would be that, okay, all the oscillators are identical, all the coupling delays are identical. So I've drawn a picture here. So these are 4 coupled oscillators. And so the general framework for discrete symmetries would be that your right-hand side basically commutes with some operation S, and that S is a group element of some finite group. Okay? So these would be discrete symmetries. And so here, this is the example. So in this case, the group would be, you can permute between like the different oscillators. So here there are 4 oscillators, right? And so that's, of course, a problem one might want to study also. Okay, so with delays, when you have delays so here we have delays in the coupling. We also have some self-coupling delay. So that means, in a sense, even though the differential equation for each component is scalar, that's just the first term, the first part here. That on its own could oscillate if you just increase the self-coupling delay. And then you have the coupling delay between oscillators, which I put symmetric here. Okay, just to, in this way, changing the coupling delay doesn't change the underlying solution, only its stability. My choice. And then so here this will be a classical example. So if you study this problem, what you encounter is, let me show you. So you will just, so for example, you vary the parameter tau c, okay? And as you vary it, you notice that your equilibrium becomes unstable. And when you watch the eigenvalues of this, you will notice that there are 3 eigenvalues, like there's a geometric multiplicity 3 in one of the eigenvalues, which is just imposed by the symmetry. It doesn't go away. And that means at your Hopf bifurcation, you got 3 identical pairs of complex eigenvalues on the imaginary axis. Okay? So it's not a standard Hopf bifurcation. And that means the tool, like a standard generic tool, would not be prepared to deal with this. But what is well known then in this case, that you can branch off in many different directions from there. Okay. So now what ddBiftool does is, so ddBiftool will not do the group theory for you. So you have to know the group theory. So you have to find that there's a general theorem, which is called, in this case, the equivariant Hopf bifurcation theorem, which tells you how you can find periodic orbits branching off there. So in this case, you would have, for example, at least, so these are the 4 we found, right? 4 different periodic families of periodic orbit that branch out from there. Okay, so remember we had 4 coupled oscillators. Is there something? Huh? Any comment? Huh? Okay, good. So anyway, you have 4 coupled oscillators. Okay, so in the equilibrium they're all identical, and so then like the type of orbits that branch out are, so for example, as you can see here, so they would all be identical, but with phase shift 1/4. Okay, or it could be the case that 3 of them are identical. This is at the bottom. 3 of them are identical, and 1 of them is different. Okay, or here 2 pairs of them are identical without phase shift within each other. So 1 and 2, 1 is equal to 2, 3 is equal to 4, or another part would be 1 is equal to 2, and 3 and 4 are equal but phase shifted. Okay? And of course, like all permutation of these would also be solutions. So there's of course like a large number of solutions, but these are the ones that are really qualitatively different. So I just plotted how they look like, and as you can see, their stability is unclear. So in this case, for example, the green one is stable always. All the other ones come out unstable, and so the quarter shifted one, the most symmetric one, becomes stable later. Okay, so let me briefly show. I just move to the next slide, and then I briefly show the service that ddBIFTOL provides, or the support that ddBIFTOL provides to produce like these kind of branches. Okay. So yeah, so that's what you have here. So by the way, so this one then here, you see this is a symmetry breaking, which you would expect. You have a symmetry, you have a periodic orbit, which still has a fair amount of symmetry, okay? Like they're all equal with quarter shift, and then that symmetry reduces further here. And then again, you can track that curve. So what is the approach that we take here? So as I said, so we do not do the group theory for you, but what we do is the following. We permit the user, so I should mention, so this is an approach that I took from, like, so Harry Dankovich has basically implemented that approach for COCO, which is this general continuation tool for arbitrary nonlinear problems. Okay, so it's just the ideal tool if you want to add equations. Okay, this is the philosophy of COCO. You can add equations, and so now you can do a little bit of this also in ddBIFTOL. So for example, this is what I wrote down here. This is the internal problem that ddBIFTOL solves if it continues a Hopf bifurcation. Okay, it finds the equilibrium, which I call xec here. It adjusts some parameters. It has the Hopf frequency, which I call omega, and it has the eigenvector, which is v. Okay, and so that problem is degenerate if you have a symmetry. But what you can do is you can just impose additional symmetry conditions. In this case, for example, on the eigenvector. Okay, and if you impose the right symmetry conditions, then this problem will then suddenly have, like, you just like add equations. And so if you add enough equations, the problem will become, like, we'll get the right, in this case, the appropriate dimension of the null space, which would be, like, initially you have a 6-dimensional Hopf eigenspace, if you like, and you have to add the right number and the right type of equations so that you get a 2-dimensional null space, and then in that 2-dimensional null space, your small harmonic orbit can lie. Okay, and that's, so you just have to find, you just have to find the appropriate fractions and the appropriate symmetry, what I call S here, this permutation, to make that happen. Okay, so the user can do that, and then what the code does is automatically adds the dummy parameters to make this again a square system, because you see now you have too many equations for your variables. Okay, so let me briefly demonstrate this for this coupled oscillator problem. Here. Okay. Here. So the way it works is, let me just run this up to, I have to stop running. Here. So okay, so this is the scenario that we had. So we have our equilibrium, which doesn't change because we just vary the delay. So at this point, we have it was a stable fixed point, and now suddenly we have 3 pairs of complex eigenvectors crossing the imaginary axis. So now we can check So for example, if we add the constraint that all, like in our Hopf eigenvector, that all components are completely equal. Okay, so if we do that, then the underlying matrix will have, like, we just check there's this underlying matrix, and what we should basically construct an additional constraint such that we get two, like a null space of dimension 2. So we compute some singular values, and in this case we see that there are no 0 singular values. So that means we cannot impose the constraint that all oscillators should oscillate in synchrony. Okay, so that's not possible in this case. So if we impose here, in this case, we impose that only the oscillators 1 and 2 are equal. If we impose that, then we get that now 4 singular values are 0. So that is too much. Okay, so we cannot uniquely branch off. Okay. But if we impose that here in this case, that the oscillators 1, 2, and 3 are equal, that would be, oh no, let's take this one. So now we impose that 1, 2, and 3 are equal, but all are shifted by a quarter. Okay, if we do this, then we see we get 2 singular values that are 0. So that means we have a 2-dimensional plane in which we can branch off according to this equivariant Hopf bifurcation theorem, and we get a periodic orbit. Okay. Similarly, then if we impose that 3 oscillators are equal, okay, again, 2. And so this is, so what the tool allows you, so if you know your group theory, so it basically what it does is it gets the linear algebra out of the way. It only does the linear algebra. You have to find the appropriate subgroups of your symmetry. Okay, so that's your job. Okay, so that's what it does. So yeah, so this is how you basically, you can experiment and find the appropriate groups, the appropriate symmetries that allow you to branch off. Okay, so that's the approach, and so that's a picture in 2 dimensions as you what we would see here. So you see, so this was our highly degenerate Hopf bifurcation. So this is the Hopf bifurcation that is when you increase the, so these are the 2 parameters, the coupling delay and the self delay. If you increase the self delay, you just discover a Hopf bifurcation that is completely symmetric. So when you branch off there, you get synchronized oscillations. And of course, when you then like increase the coupling delay there, what you encounter, for example, is something that would be a torus bifurcation, except that it has a triple Floquet multiplier on the unit circle, pair of Floquet multipliers on the unit circle, which is again very degenerate. So you can only track it if you again impose some conditions on the Floquet multipliers, and then you can track that equivariant torus bifurcation into parameters with no problem and discover some highly degenerate 1-to-2 resonance if you want. So this bifurcation diagram, I should mention, is incomplete, just for demonstration. Okay, so this is what you can do. Okay, you can track discrete symmetries. I should mention, so this was originally inspired by the work that was done by Claudia Wolf. Okay, so she knew everything about the group theory, and she had developed a piece of software for ODEs. But yeah, so this has been now partially incorporated into Coco, at least the linear algebra parts, that people can at least continue, like, work with some symmetries. Okay, so let me now move on to the final bit, which are like distributed delays. So the way it works, the way it's implemented in DDBIF tool is, so remember, we can do algebra, we can add algebraic constraints, and so that's how it's treated. So you have, so what I permit is, you can initially provide a non-square M, and that means also an F that has fewer outputs than dimension of the input. And then you add some constraints. So where you basically, what you do is you just provide the indices that enter your integrand, huh? So like the indices, which states do you need here and which parameters do you need here. And then, so what this does is, you see, this creates an equality between, like, you have one of your components, x, is basically this integral over the past, huh, of some function g, which you provide. So you provide a function g, you provide, this might also be either a parameter or it's a state. Okay, so you can introduce a state for this. This could be state dependent. It could also be, like, for example, implicitly defined. Huh? And so then that x, you see, you can use that in here. So this way you can have arbitrary integral terms inside your right-hand side. So it permits multiple nested integrals, because you see this this L here and this K can overlap. The X can be multidimensional. So several distributed delays are possible. Now, what I practically do is I just replace this integral with n, and the n is fixed with the number of discrete delays, which is just a quadrature formula. Okay, so that's what it's doing. So that's so this means it's just a wrapper around the ddbif tool. Like before you start the ddbif tool, you just create this extra function, and then it turns it into appropriately adjusted delays. And of course, what it does is, as you vary, for example, the tau d here, it varies automatically all the internal delays there, because they adjust as well automatically with it. Okay. So here's a simple example. I use it again. This is from Dimitri Breda's work on renewal equations. It's a very simple example for which one knows an analytic formula, so it's easy to check the result. And so that would be implemented in this form. Okay, so you would just have, you put everything on the other side. Your M is identical 0, the matrix, right? You just have this as your, you just introduce a variable Y, which is now the integral. Right? Yeah. And then you just have here, like you've got two delays here, and you just introduce one of the delays into your right-hand side. Okay, and so then you get a bifurcation diagram with just standard ddbif. Okay, so just a bit of a summary on why. Okay, so there you could, like, a possible alternative approach is, so I know that this is implemented by Francesca Scarabell and then Davide Liesi, is you formulate the delay equations as an abstract ODE, and then you just pass it on to MATCONT. So that is a more general approach. So ddbif can only solve a subset of those problems. So the point is that I think especially for where you have discrete delays, and if the delays are large, then probably the approach with ddbif is simply in terms of computational effort more feasible, simply because the complexity of the problem is not as large. I mean, so for example, tracking a periodic orbit for a delay equation is not more expensive than doing it for an ordinary differential equation. You simply refer back to other parts on your orbit that you have to store anyway. Okay? While as an abstract ODE, so that really treats your delay differential equation like a partial differential equation, which the partial differential equation, which it actually is. Okay? So that makes this more expensive. So that's the main difference to the more general approach. Okay, so you could view this as this. So what ddbif is doing is it is solving this PDE along characteristics automatically, like inside. Okay, so now let me just finish off by listing a few of the problems that one instantly encounters if one tries to use ddbif tool. And so they are mostly related to the problem when you want to study linear stability. Okay, so just to mention what are the methods that are used inside in ddbif tool. So that was a change by me. So the original ddbif tool used these linear multi-step based methods. They were implemented by Kuhn-Engelborgs and Kuhn-Verheiden. They are still present, but they have to switch it on as an option. So the default would be, I reverted to as a default to the methods that were introduced by Dimitri Breda. I mean, there's a standalone tool, TraceDDE, and that basically just approximates the history with Chebyshev polynomials, and then it just gradually increases the degree until the desired number of eigenvalues becomes sufficiently accurate. That's what it's doing at the moment. So it's a pseudo adaptation there. And so that turns very accurate very quickly on, as long as the problem is feasible. Okay, so that's for equilibria. So for periodic orbits, it's doing a more or less, this is the only sensible approach, which was already implemented by Kuhn-Engelborgs. And I think I've seen a paper that analyzes this approach by Borgioli et al. So you have a collocation mesh of your periodic orbit anyway. You extend this periodically all the way like to your history, okay, scaled by time. With the identical piecewise polynomials, that gives you a large linear problem, a large matrix problem, which you then just solve with either a sparse eigenvalue solver or just eigenvalues. Okay, so, and both of these are somewhat problematic. Let me just show you. So this is a toy example, so which is really setting up a severe problem, which is well known to experts, but less obvious to just users. Okay, so look at this problem here. You've got x prime is equal to minus x, minus y of t minus tau, y prime is equal to minus y. So obviously this is just decaying with rate -1. And then this is, okay, this is just one directional coupling. So you have basically a spectrum should be eigenvalue -1 with algebraic multiplicity 2. It's independent of the delay. Okay? If you try this here, then this is what you get. Okay, so I just to zoom in. So you have, so this is the correct one eigenvalue is correct. The one that is nearby, like closest to one, is also correct. So look at the scale of the imaginary part. This is quite a, like you get like a lot of the instability occurs for high frequencies. But as you can see, there's a large number of, and so this is at maximum size. So this is the highest possible accuracy. I feel like I used a large possible, like metric size 2000. Okay, and as you can see, there's a large number of spurious eigenvalues. I mean, either for small frequencies and for higher frequencies, they even dominate the correct eigenvalues. Okay. So now the good news is that this only occurs if you are to the right of the imaginary axis, or to the left of the imaginary axis. And the reason behind this is basically, yeah, so look, this is, so the delay that I chose for this example was 20. 20 doesn't sound that much, but of course, what enters your equation is basically exponential lambda times 20, and the lambda is -1 basically, so that adds up to like e to the power 20, which is gives a huge error. So there's a theoretical statement by Dimitri Breda, which would suggest that there shouldn't be a problem, but it turns out there is. Okay, so if you have an eigenvalue, then you have a theoretical convergence statement. Okay, you choose your discretization approximation of high order. That's what we do. And so then we know that they should converge for our discrete metrics to the correct eigenvalues, like according to this formula. But what happens in the demo is, okay, so our k is equal to 2. That's not so dramatic. The L is equal little l. So this is the order is equal to n. So that's pretty large. So this should be a huge number. But then what happens here is that the eigenvalue at -infinity basically has algebraic multiplicity infinity. So that means you don't really know what happens. Okay? So this is like this can encounter, you can have a large number of spurious eigenvalues. If you got like this, like if you have a chain, okay, if you have a delayed chain that doesn't connect back, then that can create these kind of problems. Okay, so this is something that happens. Another problem is when you have neutral delay differential equations. Okay, so this is a neutral delay differential equation. I think it should be stable, but you see it creates a Floquet multiplier in this case at -1. So that is like critical. Okay, and when you check the eigenfunction, it looks like on the right. So that is obviously just at the level of discretization. So that instability only occurs for some discretization. So you cannot use, so like DDBIF, you cannot use these well-known Gauss-Legendre nodes for anything that has an implicit, like where the M is singular. Okay? So, and a similar problem occurs with renewal equations. When you have a renewal equation, like even the simple example that I showed you, when you discretize when you just approximate the integral with a quadrature, with a fixed quadrature formula, then you get an equation that looks like this, which is a neutral equation, which is unstable because the sum of the weights is bigger than 1 in modulus. Okay, the sum of the modulus of the weights is bigger than 1. And so that means you must see always at high frequencies, you will see unstable spurious eigenvalues. This will always occur if you fix for a fixed quadrature rule. So you can't avoid it. So you just have to exclude it. And similarly for periodic orbits, it's a bit harder to do because the Floquet multipliers are on the unit circle. So you wouldn't be able to tell, but you can look at the eigenfunctions, and then the eigenfunctions look like this. Okay, and so then you know, so so I just run the code, found a Floquet multiplier, but I look at the eigenfunction and I know this is a spurious Floquet multiplier. Nothing I can do about it. Okay. Yeah, so just to summarize, so by the way, one other pitfall that I didn't mention here, which was studied in detail, especially that affects anybody who is working in optics. So there's a common problem if you have a large delay. Okay, anything with a large delay, there are potentially enormous problems with, like, they can easily calculate periodic orbits or equilibria even easier, but the stability gets really, really hairy. Okay, so here's a summary. Okay, so by the way, I should mention this is, I'm aiming to stay Octave compatible. So even if you don't have MATLAB, it should just run. So yes, it's mostly useful for, okay, so bifurcation analysis of simple objects like equilibria, typo, periodic orbits, with discrete delay, and delay differentiation with discrete delays. So singularities that are caused by symmetries, like symmetry breaking or so, can be treated. We just add conditions. I have also created an interface to Coco, so Coco can just deal with nonlinear equations, solve nonlinear equations. And of course, ddbifter, what it's doing is it's setting up nonlinear equations and then solves them with its own Newton iteration, but one can also just use all the numerical methods from Coco. I have a few more complex examples for renewal equations and distributed delay, as ddbifter demos. And so, so the demos are available here and the code is available. Okay? So that's all I have. Sorry for just running over so much material, but I just wanted to kind of give a summary. Hopefully there's something relevant for everyone. Thanks.
Yeah, thank you very much, Jan, for this very clear talk, an inspiring talk.